Ladies and gentlemen, please welcome Peter Barrett, General Partner at Playground Global for remarks.
For remarks. I don't know what that means. Hi, I am Peter Barrett. I am a founding partner of Playground Global. We are a deep tech venture firm based in Palo Alto. And I want to talk to you today about degrees of freedom we have to use investment in deep technology to move civilization forward. I want to start with a quantum computer. Actually, probably the world's best quantum computer at the moment. This is Willow from Google, and when this was announced last year, it added $100 billion to the market cap of Google. It is a 105 qubit machine, and it did a couple of extraordinary things. One was it demonstrated that you could actually make a quantum computer better by adding more qubits to it so it could correct its errors faster than it made them. That was a great result. It also produced a calculation that would take about 10 to the 25 years for a conventional computer to calculate. And so demonstrating that quantum machines are not only architecturally possible, but they can do things that our classical machines can't do. Now, unfortunately, the thing it did was not very useful, right? It didn't have any practical applications. So why do we even care about building these machines? And I'd argue that the reason we care is that we don't know how to do chemistry, right? The catalysts that animate our industry are discovered, not designed. We're stumbling around in the dark, discovering things rather than designing things, because we can't simulate the quantum nature of nature with classical computers, right? That our classical computers fail us in simulating drugs. We don't even know how Tylenol works. And the reason for that is the chemistry, what we do with catalysts, come from interactions of quantum systems, interactions of electrons, and every time you add a new electron, it interacts with all the other electrons in the system, and you get this exponential explosion in the computation required to calculate the behavior of these highly correlated quantum systems, right? But quantum computers are different. They are based on the same quantum mechanical principles that animate chemistry. And so there's a direct mapping between the system you are simulating and the quantum hardware you are simulating it on. And so these machines, for the first time, will be able to allow us to design things, not merely discover them. Right, there was a good example of this a couple of summers ago when it was announced that a Korean group had discovered a room temperature superconductor, which would have been a phenomenal discovery, right? Would have revolutionized, Teslas and transmission, would have utterly changed the landscape of the economy. But the announcement was followed by a flurry of activity to try and figure out whether it was really a room temperature superconductor. And so our best chemists, right, using our best supercomputers, took their best algorithms, their best classical algorithms, and tried to simulate the behavior of this material. And half of them proudly pronounced it was a superconductor, half of them proudly pronounced it wasn't, right? These are not dim people. And so it was back to making some of it, back to cook and look, to measure its properties, to understand whether it was a superconductor or not. It's more than a little embarrassing. So this is the unit cell of that material. It's an interesting material, but it's not intuitively obvious whether it's a superconductor or not. And the algorithms we use to understand its properties, to simulate its properties, are beautifully designed, but completely wrong for any highly correlated quantum systems. Here's another example of how far we are at the moment from agents. This is a series of superconducting systems that was investigated. My mic not working? Is the podium mic working? Is that better? Can you hear me now? Okay, great. So I will gesture less. So this is an example of superconducting systems that was being investigated in Japan about 2010. And the figure of merit with superconducting systems is how warm can it get and still conduct electricity with no resistance. So the lab was working on this. They had a party. One of the scientists spilled a glass of wine into the experiment, and the temperature went up. And so they literally published a paper spilling all kinds of different alcohol into the experiment. This represents how we just have no tools at the moment to explore this part of nature. That is about to change, because things like drugs, things like superconductors are the kinds of things that will animate our civilization in the future. This is an interesting periodic crystal like other superconductors. This one is a YBCO. We are using this to attempt to build fusion reactors, but we haven't the slightest idea how it works. We don't know why this particular combination of materials conducts electricity with no resistance. But we are using it to try and build our energy future. We can't model it. We don't understand it. You've probably heard much about the critical minerals crisis and our need for exotic materials to make high field magnets. Our best rare earth magnets are hard to come by, but incredibly important for making things like Teslas and other applications. This is another periodic crystal made of two of the most common elements on the planet, nitrogen and iron. This produces magnets which are far stronger than our best rare earth magnets. We don't understand why. We have no idea. But these periodic crystals are a design space which is essentially infinite, and we've stumbled across a few materials with exotic properties. But if we had a tool to engineer these things, it would be like waking up one day and finding another million elements on the periodic table that all had new and exotic characteristics. So we are white-knuckling the available of critical minerals, but a common prosaic combination, taking matter and arranging it in novel ways, will produce new physics. And there is essentially no limit to the design space that we can explore. We just don't have the tool to explore it right now. Take that nitrogen, and instead of mixing it with iron, mix it with gallium, and you get high bandgap superconductors, high bandgap semiconductors that can cut the power footprint in our data centers by a factor of 2, right? So small variations, novel arrangement of matter produces really interesting physical properties that we can explore. And so one way of thinking about this for me is to imagine a world of these quantum materials, is to imagine a world without metal, right? If we didn't have any metal, we could still have wooden houses. We could build cathedrals out of stone. We could make plowshares out of wood. We could have movable type. We could have culture and poetry and so on. But we'd have no idea what electricity was, right? That phenomena would be completely, we just wouldn't have any expectations about it existing. It just would be completely out of our experience, right? And without electricity, we wouldn't have electromagnetism. We wouldn't have Teslas. We wouldn't have X, which is probably a good thing. But all our civilization is based on a phenomena that in a world without metal we wouldn't understand or even miss. We do live in a world without metal, right? The world of quantum materials is as different to our world as the world without metals is. And we're a handful of years away from having the tools to explore that world. So here is another one of those crystalline structures. Barium titanate. It's an interesting material. Its magical property is that it has the ability to switch light. It's the most efficient way of switching light known to man. And if you take this and produce
atomically pure wafers that are dinner plate size, arrange them in a certain way, project optical components onto those by investing hundreds of millions of dollars in collaboration with one of the tier one semiconductor fabs in the world, create components, optical switches, single photon detectors, various other devices, arrange those carefully into systems, wire them together with kilometers of fiber optic cables, assemble them into cryogenically cooled cabinets. That yields a very interesting device. And that device is a utility scale quantum computer. Now, the Willow hardware that I opened the conversation with was 105 physical qubits. The machines that PsiQuantum is building out of that barium titanate and out of those silicon photonics is a machine that is 10,000 times the size of the Willow hardware. It's a million qubit class machine. And there are two of these machines under construction. One in Brisbane, Australia, with $940 million from the Australian government, and the other in Chicago with $500 million of infrastructure and another $500 million of incentives. These machines are not theoretical. These are being built. These will be the first useful quantum computers where we can run a wide variety of algorithms to answer a series of impossible questions, including how we engineer quantum materials. The machine in Queensland should be operational by the end of 2027, and the one in Chicago by 28. So we are years, not decades, away from these machines being operational. Now, hardware is not the only thing we need to consider. That, as always, hardware and software have partnered to create useful results. And as hardware is increasingly improving, so are software algorithms. And in fact, software algorithms are improving about 1,000 times faster than the hardware does, which has real implications. One of our companies, Phasecraft, have been working on how to more concisely represent the impossible questions and frame them in a way that can fit on smaller and smaller quantum computers. This is a logarithmic scale, and you can see since the founding of Phasecraft, simulation of a material like strontium vanadate, which has really interesting implications for renewable energy, that complexity is converging on the scale of our current machines. And so as we continue to push the optimizations forward, the convergence becomes inevitable and increasingly imminent. One of the favorite algorithms that Phasecraft has been working on is this density functional theory algorithm. That was the algorithm that failed to characterize the room temperature superconductor. And nearly all of this runs perfectly well on a classical computer, and you get the right answers. But there's a small portion of it which concentrates the quantum mechanical behavior of the system, and Phasecraft have a novel algorithm to run just that portion of the algorithm on a quantum computer. And we expect them this year, in collaboration with Google, to demonstrate capability beyond classical. So on even a small quantum computer, to do things and produce results in this very, very standard workhorse algorithm that exceed what would be possible on a classical computer. There's also another algorithm people care a lot about, right, which is breaking cryptography. Not my favorite application, but something that will certainly happen. There was a recent result in the last week that suggests that this is possible on about 1 million noisy qubits. That's the size of the first PsiQuantum machines. But what's most sobering about it is the trajectory of development of this algorithm, right? That these are novel new arithmetic methods that are breaking all of our current public key cryptography within reach of the machines in the next couple of years. So this is not a question of if, it's a question of when, and the when is getting closer and closer. Now, we also have this other form of computation that people have been talking about a lot. This is arguably the most complicated machine on Earth. This is an ASML machine. which is used to make our most advanced semiconductors. Now, people have talked a lot about Moore's law being dead. It is not dead, it is merely resting, and technologies like this have ways to go before we run out of steam in our conventional semiconductors. The problem with this machine is that it is starved for light. Its capabilities stem from its ability to make extreme ultraviolet light, but it can only produce a tiny fraction of what it could use. And so we are working with one of our portfolio companies to take the most powerful lasers on Earth that were created at US national labs and use them as a light source to create advanced semiconductors. And this light source is 10 times as powerful at 1/10 the power and allows us to continue to make smaller and smaller advanced semiconductors, not only to produce smaller features, to produce better transistors, but to greatly enhance the productivity of North American semiconductor fabs, right? And so this could more than double the productivity of a fab, and each one of these light sources is worth about $50 billion over 7 years because of the increase in productivity of those fabs. So this is not a theoretical technology. It exists. These things operate. They're being commercialized for applications in semiconductors. There's also completely different ways of running existing software, right? That we've been running code on CPUs and GPUs, which are 70-year-old architectures. They rely on executing instructions one by one. There's completely different ways of doing it. This is from a company called Next Silicon. It is now being designed into supercomputers in our national labs because it outperforms NVIDIA GPUs significantly for high-performance computing. And what it essentially does is take software and automatically designs hardware implementations of algorithms, and those are being used in national labs and other high-performance computing applications today. Again, not a theoretical technology. This technology ships. This technology, this image here is from a technology that's been around since last century. This is a flip-flop, a piece of digital logic that runs more than 100 times faster than our current fastest computers. It does not use transistors. It does not use semiconductors, but has the possibility to make our computation not only 100 times faster, but do so at 1/100th the power or beyond. This is superconducting logic. And once you're building warehouse-scale superconducting systems for quantum computers, you can easily imagine fitting this technology into that same framework. And in theory, I should be able to build a machine that's about a cubic meter, which has the same computational performance as a data center, right? Again, not a theoretical technology. These things are being used for classified signal intelligence applications, and they're about to be commercialized for classical computing applications. I also want to talk about biology, which is something that we do a lot of investing in, and we're all emotionally connected to it. This technology is a quantum contrast agent technology. It started off as a quantum computing technology. This falls into this quantum sensing category that allows us to see magnetic fields, gravitational fields, electric fields with unprecedented fidelity. It allows us to have navigation without GPS, to see kilometers underground, to see through, to make oceans transparent. And in this case, this technology makes ordinary MRI machines 100,000 times more sensitive. And that allows them to directly image cancer metabolism, to be able to see the differential metabolism between healthy cells and cancer cells. This is a shipping product. It is not hypothetical. These things exist and will be used in humans this year. One other technology which is moving from theory into reality is a programmable RNA technology. It allows you to actually write code to say where and when an RNA therapeutic is expressed. We have data from a clinical trial that is being presented today. And forgive me if the next image is distressing, but it shows the efficacy of programmable RNA seeking out and destroying cancer. Right? This is a melanoma patient who was doomed, but by programming RNA to replicate itself under certain circumstances has led to this rather dramatic change in outcomes for this patient. We also have work in using AI to delve into other parts of nature which have been invisible. Atomic AI can now take a genetic structure and predict RNA sequence, RNA behavior and dynamics for the first time. Again, not a theoretical technology, but something we're actually living with today. Our ability to create the minerals we need has been limited in the past by our desire to dig things up out of the ground in northwestern Australia, send them to China, take coal from the east coast of Australia, send it to China, put the coal in the atmosphere, and have a supply chain where all of our critical minerals route through one place. This is Port Hedland in northwestern Australia. It's not only the site of most of the world's minerals, it's also the best renewable site on the planet with 70% naturally firm renewables. And we have chemistries and methodologies to turn Australian minerals into valuable metals, put them on the same ships, but have them go to Korea, Japan, and the US, as opposed to going to China for processing. Working technology, we're building out this infrastructure. And finally, I want to end with probably the most important technology of all. This is photosynthesis. It was invented 3 billion years ago by accident. It was invented in a world that had a CO2 and methane atmosphere, and we've been stuck with it ever since. It has led to all life on Earth. It's an extraordinary technology, but it's far from optimal. The protein, ribisco, that is at the core of this technology is incredibly inefficient. It's only good for about 1% of turning a photon into sugars. But we have a company which has successfully re-engineered this metabolism that can double the productivity of corn and soy on the same inputs. So we're not stuck, right? It isn't a zero-sum game. We can engineer things that can change the material world, change our chemistry, change our drugs, change our catalysts. We have degrees of freedom that we've never had before. And it's a little bit like what happened right at the end of the 18th century, right? Where we were stumbling around in the dark, fiddling with things, but we were about to experience a real watershed in technology that would break open our agency over nature and our agency over the physical world. Galvani was doing experiments with frogs, and he noticed that they twitched when he poked them with metal probes. And this twitching he attributed to some magical animal magnetism. What was really going on is by using two different metals on a frog electrolyte, he was making a battery, and he was putting electricity through the frog legs, which made it twitch, right? So he'd inadvertently created a battery, but he had no idea what he was doing. But Alessandro Volta did. And he took copper, zinc, and briny cloth, and he built the first reliable source of electricity, the first battery. And this led to an explosion in our understanding of chemistry. It led to dozens of new elements being isolated. It led to electromagnetism and electricity and all of that stuff we would miss in a world without metal, right? And it came from a discovery by accident. You could have made a battery like this 10,000 years ago. We had all that elements, but it never occurred to anybody to arrange matter in that novel way and get novel physics from that matter. There are things all around us that are like that. There is matter that can be arranged to create phenomena that we cannot imagine now, but the tools to do it, quantum computation, AI, advanced classical computing, have never been more powerful, and we're at a watershed now where that world of abundance is right in front of us. We just need to see it with better eyes. Thanks very much.